All right, guys, this is the video lesson for section 10-2 in your book. This is the one that I've been referring to that can be a little bit troubling and it's kind of new. So I may even split this into two separate video lessons to make sure I have enough time to cover everything. You'll also notice that the assignment is not due until Thursday at 4, and you just have one due this particular week. So I really want you to focus on this one and learn how it works. All right, so the idea of 10-2 is it's not always going to be okay to take radicals or square roots, like the square root of 50, and just turn it into a decimal. In the real world, when you're designing buildings, when you're manufacturing aircraft, when you're determining how far it is between stars, things like that, you don't want to be inexact by just turning to a calculator and getting an inexact estimate of the square root of a non-perfect square. So what we're going to do is we're going to learn how to simplify perfect squares so that we can keep it as an exact number, still a square root, but reduced as far down as we can to make it easier to work with. Here's an example. When you have something like the square root of 160. Now, you'll notice that the square root of 160 is not a perfect square. The perfect squares are 144 and 169. Here's what a perfect square is. The square root of 144 is a nice, neat integer 12. The square root of 169 is 13. So the square root of 160 is somewhere in between there, maybe 12.5 or 12.6 if we were to estimate it. But that's not what we want. Instead, we want to leave it as a square root, but we want the number inside the radical sign, inside the square root sign, to be as small as possible. So here's what we're going to do. And there's several ways to go about this. We're going to take the number 160 and we're going to find a multiple of 160 that is a perfect square. So start and think about all the perfect squares that we know. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. You can already tell, isn't 16 a factor or a multiple of 160? But 5 times 5 is 25. 6 times 6, 36. Whoa, that did not come out good. My little marker's not working well there. Try to get rid of that. 49, 64, 81, 100, 121, 144, on and on. So we're looking for these numbers inside of square root signs. Here's why. We noted that 16 is a perfect square. So I'm going to rewrite the square root of 160 as 16 times 10. Okay? That's the same number. The square root of 16 times 10 is the exact same thing as saying the square root of 160. The difference is I've identified something that I can take a square root of. Everybody here knows that the square root of 16 is 4. So why don't we make it a 4 on the outside and leave the 10, which has no perfect square, on the inside? Now we've taken the square root of 160 and we've simplified it into 4 root 10 or 4 radical 10, as I'll sometimes say. It's just easier to say. 4 radical 10 is the same thing as saying 4 times the square root of 10. But it's a much easier number to deal with, and it's an exact number. If you were to check it on your calculator, you would find that the square root of 160 gives you the exact same decimal number as 4 times the square root of 10. And so we're going to go about doing this. So let me erase this one. Let's try another one. Remembering that we need square roots and we need to find them. All right, so let's try the square root of 72. All right, now, the first time people see this, and I tell them, okay, look for square roots or perfect squares, most people immediately see the 9, and it's 9 times 8. Okay? So the square root of 9 is 3. We're going to cross it out and pull it out because I'd rather have the regular number 3 rather than the square root of 9. and I get 3 square roots of 8. And this is where I need you to pause and not go so fast in your work. We found a perfect square 9 in 72, but it was not the biggest perfect square. The biggest perfect square some of you may have caught was 36. But we can still finish this problem by continuing on. Here's a suggestion that I have, and it's one of those things that I would normally give you as a star in your notes. So if you want to write it into your notes, here's a good thing to put into your notes. Whenever you think you're done simplifying a radical, take what's left in the radical, in this case that 8, and divide it by 4 or 9 just to check and see if you're done. Why 4 or 9? Well, guess what the two smallest perfect squares are? 4 and 9. So a lot of times, if you miss the biggest perfect square, there'll be a 4 or 9 left over inside. So let's look at that 8. 8 is divisible by 4, right? So let's rewrite 8, leave the 3 alone, as 4 times 2. Now, why would we want to do that? Because 4 is a perfect square. Everybody knows that the square root of 4 is 2. And so we're going to cross out the 4, pull it out as a regular number 2. Now, here's a question. What do we do with the 3? Do we add the 2 or do we multiply the 2? Well, the answer should be multiply, because 2 times 3 is 6, and you get 6 radical 2. Now, can't do anything with the square root of 2. Don't try to do anything with the square root of 2. It's not a perfect square. It's some ugly number like 1.4 never-ending decimal. The reason I know that this is also correct is if we had seen that 36 was the biggest perfect square, 36 times 2, then we could have immediately pulled out the 6 by crossing it out, pulling out the 6, and you can see that our two answers are the same. Okay, so there's the basics of everything. A couple of suggestions when doing this. In your notes, write down all the perfect squares from 1 to 20. What I mean by that is 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. Just like these numbers that I've written over here to the side, I would put all of the first 20 perfect squares in your notes and look at them when you're doing this assignment. Now, those of you that have outside tutors, there are other ways that teachers sometimes like to teach this. I'm okay if you choose to do another method taught by a tutor or something else you find. Usually it involves doing factor trees. The reason I don't like to teach it is if students get used to having to do a factor tree every single time, it takes a lot more time. And I'd rather you just start learning how to recognize perfect squares that are multiples of a number. Next thing is variables. We're going to take the square root of x, and we're going to think about that one first. Then we're going to take the square root of x squared. And then we're going to take the square root of x cubed, and then the square root of x to the 4th. And we're going to see a pattern here. What is the square root of x? Well, to be honest, unless I knew what x was, I have no clue what the square root of x is. So what is it? Fully simplified, it's just the square root of x. I can't simplify it any further. But what is the square root of x squared? Well, if you remember, square roots and squares are exact opposites of each other. If you've got x squared and you take the square root of it, hopefully everybody can see that the square root of x squared is just x. But then that brings us to the square root of x cubed. X cubed is not a perfect square, but it is x squared times x. And we already know that the square root of x squared is x, so that's a perfect square that can be pulled out, and you get x radical x. Can't do anything with that extra x in there. The square root of x to the 4th, well, that's another perfect square. In fact, the square root of x to the 4th is x squared. So you're starting to see a pattern here. For every odd exponent, don't you have an x left in the radical? For every even exponent that you take a square root of, it becomes a nice perfect square with no radical left over. So there's kind of a rule that this leads to. The rule is this: whenever you get the square root of a variable with exponents, divide the exponent by 2. And if it's not an even number, there'll be one variable left in the radical. So I would, if you're taking notes at all, or if you want to have notes available to use for the test, I would write that rule that I just stated down. It's going to be one that you're going to have to kind of memorize and be able to use on this next test. Now, let me give you an example. What is the square root of x to the 13th? All right, so kind of a big number here, or at least in terms of the exponent. We're going to take 13 and divide it by 2. What is 13 divided by 2? Well, it's 6.5, because one way of thinking about this is the same thing as x to the 12th, which is a nice even number and a perfect square, times x to the 1st. Well, the square root of x to the 12th is x to the 6th, so that gets to get pulled out of the radical. But that extra little x has to stay in there. Kind of a shortcut of this is divide 13 by 2. 13 divided by 2 is 6.5. The 6 means 6 full x's come outside as a perfect square and become x to the 6th. But the 0.5 means there's an extra x right here that I can't do anything about, and so it has to stay in the radical right there. All right, let's try another one. This one can be a little bit tricky. What is the square root of x to the 25th? Now, your first response is probably, oh, that's easy, it's x to the 5th. But you're messing up the rule, and you're trying to treat the variable like a number. The square root of 25 is 5. But the square root of x to the 25th is totally different. What's 25 divided by 2? Well, 25 divided by 2 is 12.5, which means that 12 x's are a perfect square. And the 0.5, you remember, if you ever get that half, it's because it's an odd number, means that 1x has to stay inside the radical. So be careful when you get perfect squares as an exponent on a variable. It's slightly different than what you've been doing previously. Let me check our time here. Yeah, about done with this one lesson. I'll do one more. The square root of 54 into the 7th. Now I've got both a variable and a number. Start with the number first. Is there a perfect square that's a multiple of 54? Hopefully everybody can see 9 times 6. And then let's just leave into the 7th alone. Okay? So what is the square root of 9? Well, that's easy. It's 3. So we get to pull that 3 outside. But let's also do the variable. What's 7 divided by 2? And notice it's an odd variable exponent, so there's going to be a variable left inside. 7 divided by 2 is 3.5. What that means is 3 n's come outside, but 1 n has to stay inside. So what I like to do is write it right back inside underneath the radical like that to remind me. Now, just look at what's left in the radical sign. We see that that 6 and that n are both left in the radical. And so fully simplified, this is 3n cubed radical 6n. We'll stop here on the simplifying part of radicals. This is a good starting place, but you're going to have to look for a second one that I will put up with the Math Excel assignment at the same time. This is a very involved section in this chapter. So you're going to have to go through multiple videos, at least 2, to get an idea of how to do it. All right. Look forward to talking to you at our virtual meeting soon. Look for another lesson to follow this one.